had to be checked, could be broken. And the reason is that along the way, starting from the Polyakov action, going all the way to the Lycon quantization, and getting rid of the negative norm states, we use a conformal transformation. And we pretended that conformal transformations were preserved by the quantization of the system. And if that was true, then we would get Lorentz invariance, because we started with a Lorentz invariant theory. Okay? So this would be true if conformal invariance was not broken by quantum corrections. So we were hoping that everything was going to work fine, and the first thing we computed gave us trouble. What was the first thing we computed? We decided to compute the spectrum. And we found that precisely something that transforms under the little group of a massless particle to give us precisely something that has the structure of a massless vector boson ended up having mass unless. So we studied the spectrum and found that we would have trouble unless A was equal to 1. Just by studying the spectrum, we found that Lorentz invariance would be satisfied. A necessary condition for Lorentz invariance was that A had to be equal to 1. So that told us that, in general, we could expect trouble, and we had to check the Lorentz invariance as a quantum algebra and make sure that it was satisfied. And that gave us a further condition that D could only be 26. Okay? So our space-time is now R1, 25. So our open string is only happy if it's living in R1, 25. Okay, very good. So the spectrum, we said there was a tachyon that was in the n equals 0 sector. There was the n equals 1 sector, and this was our gauge boson A mu. And for n equals 2, you had it as an exercise. Did you guys figure out what it is?
Treated symmetry, massive particle.
Very good. It's a traceless rank 2 tensor. And it's in the massive representation. Okay? So that ended up working out nicely. Now we want to do having succeeded with the open strings, we want to do the closed strings. So everything we did for the open strings, you guys can repeat it for the open strings. And you will find that, once again, in the Lycon quantization, we need A equals 1 and D equals to 26. So you will find the same thing. And how about the spectrum? Well, remember that in this case, we have two L0s. We have the left and the right movers. And therefore, we will have two number operators, n and its friend, the n tilde. And remember, we said that on a physical state, this thing had to be equal, and this is what we call the level matching condition. On physical states. In other words, L0 minus L0 tilde acting on a physical state must be equal to 0. So when we study the spectrum and we set n equals to 0, we have no choice but to set n tilde to be 0 too. Okay? So the mass formula is again similar to what we had before. The only difference is a factor of 4 that appears here. In the previous case, there was no factor of 4. So this acting on a physical state would be the same as n minus 1 acting on a physical state, which would be the same as n minus 1 tilde acting on our physical state. So, well, we can start the game of computing the spectrum. Yes?
Why do you need these level matching conditions?
Well, remember, everything came out from, well, first of all, remember that the alpha zeros ended up matching, right? Alpha 0 and alpha 0 tilde had to match. And second, that that this constant, this normal ambiguity, we concluded that it had to be the same because the algebra of the operators was identical. So going from the classical to the quantum theory, we cannot make any distinction between the left and the right movers. They were exactly the same objects. Now you see, remember that what we said was that the physical condition on L0, due to this normal order ambiguity, was not that the L0 had to annihilate the physical states, but we had to allow for a constant, right? So the same constant on both sides, that implies this, right? But this condition, remember, we got the number operators coming from L0, because L0 has the alpha, which is the momentum, right? So the momentum squared was the thing that gave us the mass formula. Does everybody remember how we got the mass formulas? The mass formulas come from L0, right? Because L0 has an alpha 0 squared, and alpha 0 is related to the momentum of the string, and p squared is the mass squared. Okay? So that's how we got these formulas. These ones. If you take this minus this, it's nothing but this equation. Do you remember that? Well, if you don't quite remember that, try to go back and check the derivation, yes.
So what would happen if we chose the A corresponding to L0 and L0 tilde to be different?
Well, first of all, you will find that A and A tilde will have to be equal to 1, right, independently. But there was no reason to choose them to be different from the beginning. They had to be the same. It would be very strange that exactly the quantization of the same system gave us two normal order ambiguity constants to be different. Of course, they could have been infinite, as, where are you? Oh, yeah. So our friend was asking me this morning. But, well, luckily we found that they were finite and equal to 1. Okay? So let's go back to the spectrum. We have these guys here. So the state with n and n tilde equal to 0 is just the vacuum state, right? And that means that we again get a tachyon. So the vacuum of the theory is a tachyon. Now, I forgot to say, but last time I told you that we were now allowed to panic because A was positive, and therefore we got a tachyon. But are tachyons really that bad? What is the meaning of having a tachyon? What does it mean? If you quantize a theory and you find that in the spectrum you find a tachyon.
It might mean that we have superluminal particles.
Yeah, sure. That's. But is there any physical reason why there is a tachyon? The theory is telling you that you're doing something stupid.
You're in the wrong vacuum.
Yeah, you're expanding around the wrong vacuum, right? Like in the standard model, right? When you expand around the Higgs potential on the top, right? You would think that you have a tachyon, but the theory is this is the way of the theory telling you, or pushing back and telling you that you're expanding around an unstable vacuum. Okay? So in the open string case, people studied not long ago. Well, they suspected that that's exactly what was happening, but they didn't have technology to understand what happens in the open string sector. But Sen made conjectures of what actually happens, and I think it was around 10 years ago that it was understood precisely what happens. So the open string vacuum actually decays, and all open strings are gone, and you just leave a closed string background. So that's what happens after the condensation of the tachyon in theories where you have a tachyon. And in the closed string, nobody knows. So that's an open problem still. Okay? So you still have a chance to solve something very important. What is the end point of the tachyon condensation of the closed string? Okay? So that's your homework. All right? Very good. So this is an open problem. There is a tachyon. This theory is being expanded around an unstable point. And the problem is to find what happens after the tachyon rolls and takes you to the minimum of the theory, to the true vacuum of the theory. In fact, it could be that there is no true vacuum of the theory.
Do these tachyons interact with other strings?
Yes, definitely.
So
That's what makes life interesting. Yes. Okay. Next sector. How do we construct states with n and n tilde equals to 1? Well, clearly, one way to do it is to put something like this. We have to put an oscillator with number 1, index I, any index I we like, but we also have to put an A tilde because we need both number operators to have eigenvalue 1. So these are the states. Of course, once we plug this into the formula, we find that this is 0. And therefore, whatever states are here must be matchless, must fall into representations of the little group. Now we're happy to say that it's in the little group of the Poincaré group of in 26 dimensions. So the little group is SO24. And here we got 24 square states. Is there any irreducible representation of SO24 with 24 square states? Is there or there isn't? No? Okay. Well, also from the indices, we see that it's natural that this rank 2 object, this is a rank 2 tensor, right? So it's a rank 2 tensor, and the rotations is clear that there are pieces of this rank 2 tensor which will not transform, which will not mix among themselves under a rotation. So what are the pieces? Well, if we find those pieces, we will find the reducible representations. Okay, so that's the goal, what we want to do. Yes?
Is there an easy way to check SO24 is irreducible?
That what?
SO24 is irreducible.
Well, SO24 is the group, or the algebra we want to consider, right? So what is the question? So the groups can be simple, semi-simple.
No, I mean, it is, so.
Oh, whether this representation, this rank 2
Yeah.
tensor is irreducible or reducible.
Yeah.
Well, you can classify all irreducible representations of SO24.
So it's not that much.
Well, here is so simple that we can just do it, right? So we can just decompose it in terms of irreducible representations. So we can do So clearly, if you take the symmetric part, there are so many indices and so many things to write. It's incredible. If you take the symmetric part of this tensor, right, the symmetric part will not mix with the antisymmetric part. So SO24 will keep it that. Will keep that. Okay, so you will think that this one is an irreducible representation. Not quite, almost. But it's a good start. So we split that into the symmetric and antisymmetric part. Okay? The antisymmetric part turns out to be an irreducible representation. So this one is irreducible. Okay? This one is not quite irreducible because it still contains a piece in it which is invariant, which will not mix with the other piece. And what is that? Well, that thing is the trace of this tensor. Doesn't mix with this. So we can subtract it and put it here as another piece. Okay? Well, if you wish, we can put the 24. Now, if you add them up, of course, you get the original guy. Right? We just decompose that into 3 pieces. And the claim is that they are irreducible. So this acting on the vacuum. So what is this? This is a symmetric. This is a symmetric, traceless, rank 2 tensor of SO24. This one is a rank 2 tensor, antisymmetric, and this guy doesn't have any indices left, so this is a scalar. Okay? So this is when things get exciting, right? Because you say, well, there is this guy. All these guys are massless. Remember, we're just studying the n equals 1, n equals 1 tilde sector. So if you see this guy, you would say that it wants to be nothing else but a graviton. This antisymmetric rank 2 tensor, what does it want to be? Well, it wants to be a 2 form in space-time, which people call B. And this guy, well, this guy, poor guy, all it can be is just phi. This one actually has a name. It's called the dilaton. Okay? So we find that our closed string in the massless sector has something that has a chance of being a graviton, an antisymmetric 2 form, an antisymmetric rank 2 tensor, which we can think about as a 2 form, and a massless scalar field, which we call the dilaton. Now, why do I say that this symmetric traceless rank 2 tensor has the potential of being a graviton? And why don't I say that it is a graviton?
Because it's traceless. I mean,
Well, yeah, the graviton has to be traceless. Great. It's
Why?
perfect. Sure.
why couldn't you have a graviton with some small trace?
Well, here is a trace.
Okay.
It's called the dilaton. So why don't I say, why didn't people say immediately, oh, this is a theory of quantum gravity, right? Yes, why didn't people say that this was a theory of quantum gravity in 26 dimensions?
Do we know anything about the interactions of it?
Excellent, exactly that. Having if somebody comes to you and says, look, I have a theory of quantum gravity, then you tell them, oh, how do you know? Well, because look, here is in the spectrum I have this guy. Say, have you checked the interactions? No. Oh, well then, come back when you've checked the interactions. Right. So, as I said, the goal at the beginning was to find a theory of strong interactions. So people try to get rid of this thing. But you see, it's going to be very, very hard to get rid of this. In fact, people didn't succeed. So they couldn't. And now, finally, after all this work, we're just in 1974. We have many years to still cover. When we say, well, we give up, this theory definitely is not a theory that will describe strong interactions in 4 dimensions, but perhaps it could be a theory could it be a theory of quantum gravity? Why don't we give it a shot? Okay. Now, there is something else that we have to discuss, which at the moment sounds like an aside, but it's actually very important, which is that we found that conformal invariance was very important there in order to get something that was get unitarity and get Lorentz invariance. But Lorentz conformal invariance also does something very important for us. Well, first of all, imagine, just to get things straight, if it's broken by quantum corrections, remember, this is a local symmetry. This is a local invariance, right? So what this local invariance is doing is getting rid of some degrees of freedom, right, that were there in the theory. If it's broken by quantum corrections, you cannot use it anymore, right? So whatever degrees of freedom this thing was eating up will still be there, and your theory will have these degrees of freedom. Well, it turns out that you can deal with them, so the new degrees of freedom that appear are called the Liouville field. Okay? And in principle, you can deal with that. However, if it's unbroken, of course, this will break our Lorentz invariance, right, as we said. So it will give us a theory that lives in a strange thing. But if the theory is, if conformal invariance is unbroken, we will find something nice and surprising. Which is what we're going to discuss now. So let's assume that it's unbroken and ask, well, what could be the consequences of having unbroken conformal invariance on the wall sheet? So this is, of course, so last year somebody asked me a question, which maybe I can ask you this year, just to keep the balance. So the question was, how come, remember, alpha prime has dimensions of, is a dimension-full constant, right? Alpha prime. So we have a dimension-full constant. In fact, if we ever get gravity, gravity is not a conformal field theory. So how come that we have a dimension-full constant and we still talk about conformal invariance? The answer is already written on the blackboard.
I was actually going to ask you the same question.
Excellent.
Is it that it's not conformal on the target space, but what?
Exactly that. See, I wrote it explicitly. So it's conformal invariant on the wall sheet. It's not in the target space. In the target space, we want to get gravity, and gravity is definitely not conformal invariant. Okay, and we have massive dimensions of mass. Okay, in our theory. So this is what we want to do. Now, people know that in general, in quantum field theories, if you have conformal invariance, something really nice happens. Things simplify. You get lots of constraints. If you're in 2 dimensions, even much better things happen. If you are in 4 dimensions, we now know that many, many good things can happen if you have conformal invariance. But we know that gravity is not conformal invariant, right? So you wouldn't expect to get any mileage out of conformal invariance if you're dealing with a theory of quantum gravity. However, here there is something different, because we are describing a non-conformal invariant theory in space-time using something that can be conformal invariant, right? So we can still use the benefits of conformal invariance on the worldsheet and yet describe something that in space-time is not conformal invariant, okay? But since you don't seem very surprised or very convinced that this is going to do something miraculous for us, let's actually see what it does for us, okay? I'm afraid that we will only do it in pictures, okay? But it's just to give you an idea, and hopefully you will study in more details later on. So we want to consider interactions. And we want to understand the UV behavior of the theory. Okay. So in quantum field theory, the simplest thing that tells you that there are UV divergences is already in a theory that is, say, just the simplest theory that you can imagine, lambda phi cube in 4 dimensions. Already a diagram like this will give you a UV divergence. Okay? And then this would tell you, well, okay, so there is a UV divergence. If you compute the beta function, it's not 0. And then all the renormalization group appears, and there is lots of interesting physics going on. Okay? What happens in a string theory? Okay, let's do it for our open string, which was the case that people were studying the most at the beginning, remember, with the goal of describing the strong interactions. So this picture will be replaced by a picture where you have a string coming, splitting into 2, and rejoining again. Okay. Now imagine that you had conformal invariance wasn't broken on the wall sheet. So what could you do? Well, you can use a conformal transformation to send this into something that looks like this. Once again, use a conformal transformation to, so what else can you do? Well, you can send, say, you can say that there are 2 points at infinity, one point from minus infinity and another point at plus infinity. You can send the point that is at plus infinity in this picture. You can bring it to the origin and map this to the negative real axis. So this line, let's call it like this, will map into the negative real axis. You bring the positive infinity to the origin and map this guy, so let's call it like this, to the positive real axis. And the whole description here goes into the upper half plane. And your aperture goes into something crazy. Okay? Well, we're not done yet. We now have to take that guy. Now the next step is something that must be familiar to you. You can take the upper half plane and send it into a disk, right, by a conformal transformation. So we send it into a disk. Now, the point at infinity, that was the origin, we can send it to the point 1. And the other point at infinity to minus 1. Okay? And our aperture would be somewhere there. Remember, from your conformal field theory course, these points are basically the points where we are inserting the vertex operators that describe the in and out states of the scattering. Once again, you're not supposed to follow all this thing in detail. It's only the conclusion is what I want you to see. Now there is another conformal transformation that you can use that sends this into a canonical annulus. And the price you pay for making this aperture something nice is that this point will move to some angle theta, which characterizes all the information about the aperture is almost encoded just in this angle. And, well, all the information is encoded in the angle and the radius of this annulus, of the inner circle of the annulus, okay? So we have two parameters, r and theta. So when we're doing quantum field theory, we're supposed to integrate over all possible states, right? So we integrate over all loop momenta. And the integration over the loop momenta is what gives us the UV divergence, right, when we go to high momenta. Here, we are supposed to integrate over theta and r. Clearly, the integration over r is going to be the dangerous one, right? And what regions could be dangerous? So we have to be careful with the r going to 0 limit and the r going to 1 limit. Those could be regions where we get UV divergences, okay? So if we get UV divergences, then the whole theory might just be full of them, and then we will have to add contour terms, check if it's renormalizable, and if the contour terms cannot be absorbed into the original Lagrangian of the theory, if there was such a thing, then the theory would just be inconsistent, okay? So let's see what happens. So let's take the limit when r goes to 1, right? This is an annulus of radius 1, okay? So r going to 1 is the limit when this thing looks like this. Very, very thin annulus, okay? Now, once again, we can use conformal invariance. And as we send r to 1, we are sending this epsilon to 0. So we can do a conformal transformation where we now keep the width of this band fixed, say at pi. Okay? And if we do that, the conformal transformation will tell us that as we take the limit, this thing will extend to plus and minus infinity. Okay? And it describes, so what I'm doing here is keeping now this fixed, using a conformal transformation to keep this fixed. And what the price that I pay is that the length becomes infinite. But this is nothing but the propagation of an open string from minus infinity to infinity. So this is the propagation of a physical state. And this is definitely what we call an infrared process. Okay? Now, does it give a divergence? Yes, it could give a divergence, but it's an infrared divergence. Remember, what we're afraid of are UV divergences. Infrared divergences are okay because they have a physical meaning. So when we compute any S-matrix element, we have to compute S-matrix elements and allow for all the states that we cannot measure, all right? Defining, in a theory that has massless particles, defining a state asymptotically is something that cannot be done physically. So you have to define wave package, and they all include an infinite number of states with very, very small momenta. And those divergences all end up canceling out. Okay, so infrared divergences cancel out. Okay, very good. You would say, well, this didn't look like a very short distance divergence anyhow. You're going to be in trouble with the other one, right? R going to 0 will definitely give us something that looks like a UV divergence. So let's do r going to 0. So this is dangerous. So when r goes to 0, this is what it looks like. So this distance is going to 1. Let's call it d. It's going to 1. The radius is going to 0. But now we can use another conformal transformation. What conformal transformation will you use? Well, looks nice to think about conformal transformation where if you look at the radius of any circumference in this disk, there is a conformal transformation that allows us to keep the radius, to keep the length of any circumference in this disk constant. Okay? So we're going to do a conformal transformation so that the length of all circumferences is constant. Not only is constant, let's say is equal to 2 pi. Okay? Well, you would say, well, that's fine for these guys here, but you're sending this one to 0, right? So when you're sending this one to 0, the conformal transformation, the only way to keep the structure of this thing would be to send this point actually to infinity. So this will start to look something like this. So you want to keep this one fixed. And then in order to keep the length fixed, you will have to start sending this thing. As you send it to 0, you will have to send it to infinity. Okay? So you will go farther and farther away. And this thing will end up looking like an infinite cylinder. Well, what does it look like now? It looks like the propagation of a closed string. And this, once again, is an infrared divergence. And this, by the way, answers the question that we were asking at some point last week. Well, if we only have open strings, why do we worry about gravity? Well, the reason is that even open strings have gravitons in them, okay, because they also have closed strings. And we just realized that these states will be propagated there. And the states contain a graviton, or what we would like to call a graviton. Okay? So if we could only prove that conformal invariance all the time maps something that looks dangerous in the UV to something that is just an infrared divergence, what would we get? We would get a theory that is finite in the UV. So this means that we could get and if our friend there turns out to be a graviton, then we would really get a UV finite theory of gravity. So that looks like something very exciting. So our next goal is to find out if this guy has a right to be called a graviton or not. Yes?
I don't quite understand why these propagations give us IR divergences.
Well, because you see now these are interpreted as states that are just propagating for a long time. So these are just propagations at very, very long distances. Okay. So remember, UV divergences have to do with the structure of very, very small distances, right? And these guys, actually, we were able to map them to something that is just a propagation of a state at long distances. Okay? As simple as that. There is nothing fancier.
And why was it we didn't worry about IR?
Oh, because when you define the S matrix, right, and you have a massless theory, you know that any detectors that you can have will have some finite resolution. So if the theory has massless states, every time you pretend that you are sending some given particle, you can actually produce an infinite number of particles with very, very small momenta, right? Because you have a massless theory, so you can produce many, many soft particles. So you have to take that into account. You have to compute what happens when you have a finite resolution of your detectors, and then you should allow for all those guys. So now those guys at tree level will give you a divergence because you have an infinite number of them. And that divergence happens to exactly cancel the divergence in loop corrections. So we know exactly how that happens in quantum field theory. All these infrared divergences resum. We know how to control them, and they are there for a physical reason to give us a finite S-matrix element when we compute something that looks physical. So it's just spectacular. The whole thing works out nicely.
Question?
Yes?
So is infrared divergence somehow related to confinement, or?
No, it would be in fact, it's the other way around, right? So in QCD, you would expect infrared divergences, right? But non-perturbative effects manage to produce massive objects.
No, no. So my question is, if you have infrared divergence, would you always get this kind of papers?
No, gravity has infrared divergences, right? A theory of massless particles. So gravity in 4 dimensions has infrared divergences, tons of them. It also has UV divergence. That's the problem, right? Well, who knows about n equals 8? Maybe. We will see this year, as I told you. Okay, pretty good. So now let's move on to see if we can justify the name graviton. So in order to do that, let's consider, so let's go back to our action, or to Polyakov's action. But now, let's allow our scalar fields to interact in any way they like. Okay? Well, this is another quantum field theory in 2 dimensions. And we know that the way we interpret this quantum field theory in 2 dimensions is as the propagation of strings on a target space with this metric. So that would be the interpretation of this, is the metric on the target space. But at the moment, it's just a self-coupling. We're allowing a self-coupling of our scalar fields, okay? And we want to do quantum field theory for this theory. Now there is something interesting to do, right? Because now there will be interactions. Because this guy depends on the scalar fields. So how do we do that? Well, the first thing is that we want to do it in perturbation theory. Well, this is a nonlinear theory, and we don't even have a canonically normalized kinetic term. We don't even have something that looks like a kinetic term. So we want to do that, or we want to produce something like that, and the way to do it is to quantize the theory around some particular point for some particular value for the scalar fields, which we're going to call x bar. So these are just numbers. We just choose some particular value, and we're going to quantize around that particular value. It's like choosing expectation value for these guys. The quantum fluctuations we're going to call them y. And we want to treat these guys as if they were scalar fields. So it would be nice to remove the dimensions we gave to x by just pulling out a factor of the square root of alpha prime. Okay? So we're going to expand this action and treat it as an action for y. So once we do that, what do we get? We get something that looks like 1 over 2 pi So here we get the y's immediately. Because these are numbers, derivatives will kill them. So we just get this, and we get g mu nu evaluated at x bar plus square root of alpha y. Okay? Well, we want to do perturbation theory, so we can assume that y is very small, and we can expand this in Taylor series. So this comma means derivative with respect to x rho. Right? Now we plug that in this action. And the first term almost looks like something that is canonically normalized. Right? So this guy, together with the kinetic term here, give us something that looks like g mu nu of x bar del alpha y mu del beta y nu. And this almost looks like something that is canonically normalized, except that it's mixing all the scalar fields. Remember, the y's are scalar fields. And this metric, or these metrics here, is mixing them. Right? Wouldn't it be nice to just diagonalize that? That would be the first step that you should do. If you're dealing with this quantum field theory, you should try to diagonalize that and then work with just canonically normalized and canonical kinetic terms for the scalar fields y. Right? Now, it turns out that, well, there is a nice trick we can use, and probably you have used it already. Whenever you are in GR and you're interested about what happens at a given point in a curved manifold, and you only want to know what happens on that point and things that happen around that point, what is the best choice of coordinates that you can use? They even have a name. They are called?
The normal coordinates?
Yeah, the normal coordinates. Yeah. Just to be nice to Riemann, we can use the Riemann normal coordinates. Okay. And if we choose those coordinates to start with, we can now write the expansion of the metric around a point where we choose the Riemann normal coordinates. It's always going to look like flat space-time plus a correction. And the correction is controlled by what? Is it controlled by what tensor?
Second derivative of the
With the Riemann.
Yeah, it's actually controlled by by Riemann. There are probably some constants here, like a factor of 3 or something. But what I want to get doesn't depend on that. So this is a first correction. And know that the indices know how they work out. So we have mu, nu here, and rho and gamma here. Okay? So that's important. So once we use this, we get something that looks like a nice. So in these coordinates, this thing just gives a nice kinetic term. Of course, it would be nicer if we were working in Euclidean signature, right? But let's pretend that let's not worry about that for the moment. Let's look at the interactions, okay? So that would be the free part. Now we look at the interactions, and what do we get? Well, let's look at the Lagrangian here and plug in the interactions. So we get the interaction Lagrangian looks like what? Looks like alpha prime, r mu, rho, nu, gamma, evaluated at x bar. Okay? So these are just a bunch of numbers times y rho, y gamma, del alpha y mu, del beta y nu, and we get this contraction. So let's also take on the wall sheet, let's not worry about the metric. We can take the flat metric if we want for the moment. Okay? So we have this contraction there, and this is our interaction Lagrangian. Now we can go back and ask, well, what are the divergences? Let's do perturbation theory. And we want to compute, what's the goal? The goal is to compute the beta function of this theory. In order to compute the beta function, what we have to do first is to see the correction to the propagator. Okay? So we look at the propagator, and it will have a correction due to this term. But what are the Feynman rules? Well, this guy will give us something that looks like a quartic vertex. Okay? So if we have mu, nu, rho, and gamma, this thing will have a coupling of the form r, mu, rho, nu, gamma of x bar, alpha prime. Now, if this guy has some momentum, k, remember this is in 2 dimensions, so this momentum is really a 2-dimensional guy, but it has an index mu. And this guy also has an index, which we call it nu. If these guys have this momentum, these derivatives translate into momenta. So we will have to put them here. And they have an index alpha that is contracted. So the index alpha is a 2-dimensional index, just like this 2-dimensional index here. Okay? So that's our coupling. Now, if we have our propagator, the correction to the propagator using this theory would be something that looks like this with our quartic coupling. So we'll have mu and nu. We have k going here. And we have some loop momentum, which we can call L. Okay? So this is the thing we want to compute and see if it's divergent. Okay? So what can this possibly be? Well, let's just use our interaction vertex. So this guy over here would be something of the form, first of all, it's proportional to alpha prime, of course. It has r mu nu rho sigma. K, the momentum k, right? Remember, we want these guys to be the ones with the derivative. because we're computing the correction to the propagator. So it would be something that looks like mu alpha k mu alpha times the integral, whatever the integral is. Well, but now look at these indices, gamma and rho, right? The loop is telling us that we have to contract the indices gamma and rho. And what did I do? Well, I changed the name here. So these were called rho and gamma. And we're supposed to contract these two guys. So let's put here an eta rho gamma. Okay? Remember, the contraction comes from the first propagator. And the first propagator has an eta mu nu. That's how we get this eta rho gamma here, that will contract these two indices, times the integral, which is a two-dimensional integral. We are in 2 dimensions. And it might be divergent. So we have to put a cutoff, momentum cutoff lambda. Is this clear? It might not be clear, but hopefully if you sit down and do it carefully. So let's see. You would be clear. Now, can anyone tell me what's the divergence of that integral? What kind of divergence? Maybe it doesn't diverge, or as lambda goes to infinity. It's logarithmic. Very good. So this has a logarithmic divergence. So we say integral d2L over L squared lambda goes like log of lambda. Of course, this doesn't make much sense just like that, so we have to introduce a scale. So here is a problem about the scale, because in quantum field theory we call the scale mu, but mu is the index that we have all over the place. But still, the only solution I found was to call it mu s for a scale. Okay? Sorry, didn't come out with anything better. So let's call it mu s. So what do we find? We find that we have that divergence. So if we have this divergence, we have to add a contour term to our action in order to get rid of this. So we have to add something so that when we put it here, we cancel this divergence, right? We have to add a contour term. What contour term do we have to add? Well, note first of all that this guy looks very interesting here. This guy, remember, this is antisymmetric in these two indices and antisymmetric in these two indices. So I could write this as R rho mu nu gamma nu with a rho here, right? Because we're contracting rho and gamma. And you recognize what this thing is, right? This particular contraction, you see where it comes from. It comes from this loop. In the loop, we have to contract those two indices, right? So that nicely gives us Ricci. Okay? So that contraction contracts two indices of the Riemann tensor, precisely the two that we have to contract to get Ricci. So what do we have to add to the Lagrangian in order to cancel that divergence? Well, the Lagrangian started. The free part started with this metric, right? Well, which is eta, if we wish. But eta mu nu, but never mind. So what do we have to do? If we shift this guy, remember, these guys are nothing but coupling constants, right? In the Riemann normal coordinates, it's just eta mu nu. But if you think about them, they are just numbers, and they are telling you how the scalar fields couple. So these are just coupling constants. In order to cancel the divergence, what we have to do is to add to this a term that looks like alpha prime times r mu nu of x bar times the divergence. Maybe a minus sign. So I'm not worried about the minus signs or factors of 3 or 2. There will be something here that has to be put so that when you now redo the calculation, you will find something that cancels this divergence precisely. Okay? Note that it will, because this guy will now be contracted with the two derivatives, right? So what we're doing is putting it here. We're adding it here. So then now the new piece will give us these two guys with that object. And those two guys, the two derivatives, will produce the two Ks. So it will precisely cancel the divergence of this thing. Very good. So now we're almost done, because these are the coupling constants. And remember, our goal was to compute the beta function of the theory. So the beta function measures how the coupling constants change, okay, and how many coupling constants we have, as many as indices we have here, or different combinations of indices. So we have one coupling constant per pair of index. So we have one beta function per pair of index. And this thing is nothing but mu scale, or the logarithmic derivative with respect to the scale, of our coupling constant, or our new coupling constant, right? At least at one loop, we know that this is a new coupling constant. And what is this? Well, we just computed. It's alpha prime r mu nu x bar. Okay? So that's the computation of the one loop beta function for this theory, and that's what it is. Now, remember, we want this theory to be conformal. For a theory to be conformal, what should happen to at loop level, at quantum level, what should happen to the beta function? It should be 0. It should vanish, exactly. So conformality and this means that this only happens if our space-time satisfies Einstein's equations. Remember, in this space-time, we don't have anything but the metric. At the moment, we don't have anything but the metric, right?
No strings?
Yes, so the strings are sourcing the metric. That's true. But we don't have any other kind of excitations, meaning we don't have fermions, we don't have scalars. We're not exciting the dilaton. We're not exciting the B field. We're only exciting the metric. And therefore, this is a theory, what we would call vacuum. This is a theory in the vacuum. And these are precisely Einstein's equations in the vacuum. Yes?
Okay, so I mean, previously you said that we have conformal invariance on the worldsheet, whereas here you're on the target space.
No. This theory is not conformal, right? The target space theory is not conformal.
Yeah.
This is a beta function in which theory? What quantum field theory are we doing here? This was an integral in how many dimensions? 2. We are asking look how insane this is, right? We are asking the beta function at one loop, a quantum correction, right, to vanish in a 2-dimensional quantum field theory. It so happens that we have as many beta functions as indices mu nu. Just a coincidence. And the way to cancel that beta function at one loop is to ask precisely for our space-time metric to satisfy the vacuum Einstein equations. So who said that gravity was inconsistent with quantum mechanics? That's a stupidity, right? It's coming from quantum mechanics. It's a one-loop correction. Yes?
Yeah, I don't know. I'm not so surprised. But is there a way that you also get Einstein's equation if you add matter? Does that also follow if you have strings describing particles?
Yeah, very good. I mean, so you ask, so we have to do it, right?
Did you get all that stuff?
Yeah, it would not be polite not to answer your question. So even though we're over time, Sorry. I hope your friends agree that it would not be nice not to answer your question. So let's first of all add more interesting stuff to this theory, right? At least the massless guys we know are there, right? So that would be part of the answer. So that would be the action on how the dilaton and the B field will couple to the string, or how they will look like in the two-dimensional quantum field theory. So this is a first step. At the moment, we don't have fermions. Sorry, that will have to wait until tomorrow. But let's do what we have at hand, OK? So we have these guys. And we say, well, once again, let's repeat the whole computation and compute the beta functions. So the beta functions, we will have one for these coupling constants. Okay? We just computed the first piece as if the other pieces were not there. But if we did the whole computation, we will find something like this. Here, H is something interesting. We will discuss it more tomorrow. But if you think about B as a two-form in a space-time, H is nothing but dB. So H is what? If B is a two-form, dB is a three-form. Now we can compute the beta function for these couplings in the two-dimensional field theory. Okay, and the last one is beta phi is equal to alpha prime minus a half where this H squared is just the regular contraction of all the indices of H with itself. Okay, so it's mu nu rho with mu nu rho. Now that's what you find. If again you impose conformal invariance, you will have to impose that all these things are equal to 0. So they look like the equations of motion for a bunch of objects, meaning the two-form and the scalar coupled to a metric, coupled to gravity, in our 26-dimensional space-time, right? Now, if somebody hands you a bunch of equations of motion, right? Do you think, is it always possible to derive an action from which these equations of motions arise? Is that in general true? It's very non-trivial, right? The equations of motion will have to satisfy some integrability conditions in order to ensure that they come from a Lagrangian, right? So here is the final miracle that I want to tell you today about. Which is that indeed, these equations of motions satisfy those integrability conditions, and they come from a Lagrangian. So the beta functions equal to 0 turn out to be field equations of a 26-dimensional theory. So the beta functions one loop. Okay, we only did the one loop computation. Classical gravity theory plus B field and a scalar. And that theory looks like this. So that's the second miracle. Not only they come, equations that look like equations of gravity, but they also come, they integrate into a single Lagrangian. Okay. So given that we have our massless rank 2 traceless tensor, and at low energies reproduces the classical equations of gravity, I think we can now declare that our G mu nu was really a graviton, okay? And that this theory really knows about quantum gravity. Yeah, I think we can stop here. Tomorrow we will continue with this action and then incorporate fermions. Yeah, of course. If we don't put fermions, then what kind of theory this is, right?